This lecture series is going to focus on an introduction to VHDL using Vivado. The design that we're going to be using is a modular design, a modular hierarchical design that uses a 1-bit comparator to build into a 3-bit comparator. A comparator is a device that tells that if one number is larger than another or less than another. In this case, we're ultimately going to be designing if an output for less than if x is less than y. So this device is a block diagram for a comparator for a 1-bit x, a 1-bit y. There's going to be a greater than input signal that will tell if the previous bit is greater than, and a less than input signal that tells you if the previous bit is less than. So in practicality, this is because we're going to have 3 bits that are first going to compare the largest bit of a number called x and the largest bit of a number called y. If those numbers are different, we will already know the answer if it is less than or greater than. If they're the same, then we need to pass that signal on to the next comparator and evaluate if that column or that bit, the 1 bit of x and y, are the same, or can we determine if it's less than or greater than? So if we have this situation where x is 1, 0, 1 and y is 0, 1, 1, what that means is x is greater than y. We already know this. However, the design doesn't know this, so let's evaluate what happens. Well, in the first one, we're not going to have an ln input, so when we connect that, we're going to connect it to 0. It's going to be off because there is no previous bit. So it will look at x2 and y2. X will be greater than, which means we want this greater than output to be true, which means the next bit doesn't even have to make a decision. It will just propagate that greater than through the end, and we're done. However, if the values are the same in that first column, so in this case 1, 0, 1 and 1, 1, 1, y is now currently actually greater than. So what will happen is this x2 and y2 will evaluate the same, so neither the greater than nor the less than will be true. So that will communicate to the second comparator that you need to find out if x1 is greater or less than y1. So here in this example, x1 is 0 and y1 is 1. So x1 is in fact less than. So the less than output would become true. The smaller bit would say, I don't need to evaluate, so I'm going to propagate that less than out, and my number is in fact x less than y. So here's the function. Now let's bounce up to this stage of things. This is where we have the truth table that describes that function that I just did. So I have the greater than input, the less than input, an x and a y. I have grouped them this way because it turns out the easiest way to describe it. If neither of my inputs are true, gi or li, then that means that this particular block needs to perform the evaluation, meaning that less than will be true if and only if x is 0 and y is 1. Greater than will be true if and only if x is 1 and y is 0. In the next 4 groupings is the case where it receives a previous bit that is informing that it is less than. So what that means is we don't need to do that comparison because the number has already determined that it is less than. So the output less than is 1 and the output greater than is 0. The opposite is true if we receive a greater than. The previous bit was bigger, so this bit doesn't care, and we're going to propagate that greater than to the output. We should never receive both greater than and less than because that doesn't make sense that a previous bit would be both. So we put don't cares in the output because that's not a situation that should ever occur. So here are my 2 K-maps that would result from this. They're a little bit incomplete, and I need to specify this last one because the 1 is wrapping around with this other 1 and to have a complete K-map. So what we can do is write the expressions for what these K-maps result from these implicants. So I have added the values of the x and y for each of the rows and columns so that it's a little bit easier to tell what's happening. So in the case of this is the less than K-map, we're going to say that less than is equal to Well, let's use the red implicant first, which we're going to look at what doesn't change across the implicant and keep it. Remembering that because I'm circling the ones, that means I'm creating a sum of products form. So that means that here across these rows, the one doesn't change, which is the Li. So we have less than input, or if, well, here we have greater than, gi is true, gi is false because it's 0, so not gi, and both x and y don't change, so not x, not y. So I'm going to have to add some bars over these, which I should have prepared beforehand, but the not gi and not x. Make those black texted. And maybe a smidge thicker. And there we go. That is my expression for less than, which is saying that, well, that's just this one, right? Greater than is 0, x is 0, y is 1. That makes the less than output. It's kind of an intuitive result, but that's how you would get it from the K-map. Similarly, we can do the greater than output, which I'm going to do down here, GT, which is going to be this implicant. So either greater than is true, GI, because that's the only thing that doesn't change, or, well, this is the wraparound. So here we have, on the wraparound, it's 0 to 0, so not less than, and x is true and y isn't true. So I'm going to snag these bars that I already created, bring them down, and put them in the proper place. So this is accounting for this greater than, where, well, it doesn't care about GI because that's taken care of by this term, but the less than is 0, x is true, y is false. There we go. Those are my two expressions for less than and greater than. So now that I know what a circuit looks like, let's go ahead and move into the VHDL design of this device, which is going to be covered in the next video.